Now we will use the example that we used in a previous video. And what we said is that we measured 5 million people in our town, and we found that 2 million of them were within a height range of 160 and 170 centimeters. And we call that the relative frequency of people within this height range. Now, if I tell you that the population of our town is more or less 5 million people, it means we've measured all of our people in our town. So we will not call this relative frequency anymore. We will call it the probability. What we would like to do now is we want to make a graph to see the probability of meeting people of different heights as we walk down the road. For an example, we want to know the probability that someone between 120 or 130 centimeters or 150 or 160 centimeters is. And let's draw that graph. This is the x-axis. That's our graph. And let's say this is the y-axis. This graph looks like a bell, and it is known as the normal or Gaussian probability function. It is called a function because it takes a unique and different value for different heights. So, for example, let's say that the mean value is 170 centimeters. It will take a unique value. So y will be a unique number. If you want to see the probability that someone being between 140 to 150 centimeters, that would be a different value. The x-axis represents the heights, which is our variable, and the y-axis represents the probability that a height happens. We call it Gaussian because it was developed by the mathematician Friedrich Gauss. We also call it normal, mainly because many natural phenomena, like the height of people, are distributed normally, i.e., they follow this bell shape. This is a simple term for describing a function. So distribution is a simple term of describing a function. So instead of saying the function of the probability relative to the heights, so the function of the probability relative to the heights, we say the distribution of the heights within a population. Some defining properties of the normal distributions are the following. 1. There is a line of symmetry, which is here. And the line of symmetry, as the name suggests, cuts the distribution into two halves. Also, the line of symmetry goes through the mean value of the population. And that makes sense because it says that the probability, which is here, of meeting someone with a height of 170 centimeters or someone with a height close to 170 centimeters is larger than the probability of meeting someone with a height between, let's say, 140 to 150, which is further away from the mean. Second interesting fact about the normal distribution. 95% of all measurements, so let's say that this is 95% of all measurements are within plus or minus, so this here is plus 1.96 standard deviations from the mean, and that here is minus 1.96 standard deviations from the mean. So 95% of all measurements are within plus or minus 1.96 standard deviations from the mean. The other 5% is here. So this would be 2.5% of measurements, and this would be another 2.5% of measurements. And these measurements here, we call them extreme. So these people that have these heights here are extreme possibilities, extreme values. What is the standard deviation though? Well, you may remember from high school that the way of measuring the variance within a distribution is a standard deviation. The standard deviation is a measure of how far away the measurements are from the mean. You can look this up later, but what is important for now is to remember that in a normal distribution, 95% of the measurements are within plus or minus 1.96 standard deviations from the mean. All other measurements can be considered extreme or very rare. So we know that the variable height on the x-axis follows the normal distribution. This distribution helps us find the probability that the height of the next person we meet is within a specific interval. However, in statistics, we don't use measurements of individuals usually. We tend to use mean values of a sample of individuals. So it's more practical for us to know the probability of the mean height of a sample of people. As an example, we would like to know what the probability is that if we randomly select 30 people from our town, their mean height will be between 160 to 170 centimeters. So, to represent that graphically, let's say that this is our population of 5 million people, and we want to know what the probability is that we select 30 people randomly and their mean height is between 160 to 170 centimeters. To find this, we would need to take many random samples of size 30, many of them. And then we would plot the results in a graph. This graph will give us the probability that if we randomly select 30 people from our town, their mean height will be between, say, 160 to 70, or any other interval we choose. And how would such a graph look? Let's draw this graph. So now the x-axis represents the mean heights of our samples, not the heights of individual people. And the x-axis represents, again, the probability that we find such a mean value. You may have guessed it, this curve will look exactly as the previous one, will be a bell-shaped curve representing a normal distribution. So it will have an axis of symmetry. In other words, the mean of all possible samples of size 30 from our town will be distributed normally. Now, a very interesting fact here is that the mean of many samples of large enough size will always follow a normal distribution, regardless of how the variable we are measuring is distributed. For example, even if the height of the people here, so even if the height of the people here was not distributed normally, the distribution of their sample means will follow a normal distribution. And this is part of what we call the central limit theorem. Another part of this theorem says that the mean of the sample means, so this value here, we will call it the mean of the means, is the same as the mean of the whole population of the individuals. So if we go to the graph of the individuals, we said that the mean was 170. So if we take multiple samples of these individuals and we measure the mean of the heights in this sample, and then we take the mean of these means, they will be 170 centimeters. And this makes sense. If you think about it, what it means is that taking a sample of 30 people whose mean height, so the mean of this sample, is close here to the population mean, which is 170, is more probable, it's more probable because the probability here is higher than getting another sample of with another height mean. So we now have a graph that can tell us the probability of selecting a sample of size 30 with a specific interval of heights. We call this graph the distribution of the sample means. So this is the distribution of the sample means. And we know that its mean will be the same as the mean of the individual measurements of heights in our population. Now, like every other distribution, it has a standard deviation, SD. But in this situation, we just have chosen to call it a standard error. So, the distribution of heights in the whole population has a standard deviation, and the distribution of the means of heights in the same population has a standard deviation that we call the standard error. Now, this standard error can be calculated if we know the standard deviation of the population. So the standard deviation of the population here, let's call it with the Greek letter sigma. The standard error, we call it SE. Standard error is sigma divided by the square root of the sample size. All right, so if you have got a distribution of sample means of sample size 30, so you got many samples of individuals, of 30 individuals, and you drew the graph of the probability of their means, then if you know the standard deviation of the population, you can calculate the standard error, which is the standard deviation of this distribution here. Let's now say that we randomly select a sample of 30 people from a population whose mean height is 180 centimeters. So we have a sample of size 30 with a mean height of 180 centimeters. And this would be, let's say, 180 here. Also, let's say that the standard deviation of heights in the population is 7. So sigma equals 7 centimeters. Now, this means that we can calculate the standard error. The standard error will be 7 divided by the square root of 30. Now, to make to make things easier for us, we will just say that the standard error is almost 7. Right here. We have said that the distribution of the sample means will have the same mean as the distribution of the heights of the individuals here. So the mean of the sample means will be 170 centimeters. Also, we have said that the sample means follow a normal distribution, which means that 95% of the samples will have a mean within plus or minus 1.96 standard errors from the mean. Let's show that graphically. So 95% of the population, which let's say is here, of the population of sample means now, not of individuals, is within plus or minus 96 standard deviations from, but we call standard deviation standard error here. So this is 1.96 standard errors from the mean, and this is minus 1.96 standard errors from the mean. Our sample's mean is 180, which is 10 centimeters from the mean. So it's 10 centimeters from the mean. That means that it's almost 1.43 standard errors from the mean. Why? Because the standard error we said is 7, and 1.43 times 7 is almost 10. So we have this graph here. Let's draw it again to make it a little bit more clear for us. This is the mean of 170 centimeters. This is 180, which is the mean of our sample. And we found that this is 1.43 standard errors from the mean. I don't know if you've heard of the term test statistic. 1.43 here is the value of our test statistic. So we just carried out a statistical test, and the result was 1.43. So the test statistic is how many standard errors our sample mean is away from the mean. Why do we want to know this? Well, because if it is more than 1.96 standard errors away from the mean, what did we say? We say that this is 1.96 standard errors away from the mean. We consider it, if it is more than that, it is away more than 1.96 standard errors away from the mean, we consider it an extreme value or an extreme sample. Also, we consider it an extreme sample if it's more extreme than minus 1.96 standard errors from the mean. So if it's here, that's also an extreme sample. Because 95% of the samples must have a mean value, a mean height within here. And we found that our sample has a mean value that is 1.43 standard errors away from the mean. We know that the probability of being here or here altogether is 5%, isn't it? Because the probability of being here is 95%. Or else the probability of being here is 0.05. So the probability of getting an extreme sample is 0.05. Our test statistic was 1.43. But what if it was 1.5? For example, let's say that it was here, which means it would be 1.5 standard errors away from the sample mean. That would mean that our sample mean would be further away from the mean of the population of means. The larger the test statistic, the further away our sample mean would be from the population mean. And we know that the further away from the mean, the more the probability it is that we have selected an extreme sample. For example, we know that if our test statistic is 1.96 or more, we would definitely have selected an extreme sample, because the probability of the test statistic being more than 1.96 or less than minus 1.96 is 0.05. So what if we could calculate the possibility, the probability that our test statistic is more extreme than 1.43? That would be the probability of our sample being here or here. If the probability of that, let's say, p equals 0.07, which is more than 0.05, then we know that our sample is not an extreme sample, because to be an extreme sample, the probability of getting it must be less than 0.05. So we know that our sample is within the 95% of samples. This probability of 0.07 which is the probability that our test statistic is equal to or more extreme than what we have found, is what we call the p-value.